Hi, everyone. So yeah, I'm going to be doing a multi-phase geochronological approach to look into the early evolution of Himalayan origin. So exploring metamorphic terrains are a great way really to understand rates and timing of processes during orogenesis. And so the Himalayas is a very well exposed, actively forming assemblage, and it has a well-constrained kinematic framework. So is a suitable place to study this. So the GHS represents the main metamorphic belt of the Himalayas, and that's shown in pink here on the map. And so that's bound to the northeast by the South Tibetan Detachment, which is a normal fault, and to the southwest by the main central crust, shown there. My field area is located in northwest India, so it's on the northwestern side of this map here, shown in this box. And some other areas I'll reference during the study is the Zanskar Valley and Himachal Pradesh, so just keep those in mind. Most of the GHS equilibrates later during the orogenic cycle, and this occurs under higher temperature, lower pressure conditions, so in the sillimanite-grade zones. And the issue with this is that it overprints much of the early fabric development and crustal thickening story in the origin. It's also dominated by Oligocene to Miocene metamorphic ages, and that's sort of interesting really because it contrasts with the early age of constant collision at around 55 million years. The Suru Valley, relative to other areas of the GHS, shows widespread relative lower temperatures and higher pressure, so that's kyanite-grade conditions. And that we associate with the early crustal thickening record in the origin. So this is a simplified map of my geological map of the Suru Valley. And I've just highlighted some key features on here. So we have in black is the Zanskar Shear Zone, which is the local term for the South Tibetan Detachment. And so that's our normal fault. And then we've got the lithological colors on here, and then we've got Barovian metamorphic isograds in red, and that's from low grade at biotite up until high grades at sillimanite. The sillimanite K feldspar zone is just off the edge of this map, it's about 10 kilometers to the south. So the Suru Valley is great here because we can really look at all metamorphic grades and interrogate the geochron from that. Various field seasons that I've undertaken in the area have allowed me to constrain the phase of deformation and fabric development. So the S2 is the main regional fabric, but we can see the bedding and primary metamorphic fabric there is developed. And the refolding of these fabrics to develop our S2 fabric, we can see is developed at the centimeter, meter, and also kilometer scale there. These annotated panoramas we see on the right here, the colors on here correlate back to the map lithologies. But we can see a series of tight isoclinal folds through here, and those are F2 folds which are associated with that fabric development. So all these folds we relate to the early crustal thickening that's developed in the region. So keeping that in mind, we're just going to go a smaller scale here. This chart is just going to summarize the microstructure relative to the deformation phases. So what we can take from this is in both metasedimentary and metavolcanic rocks, there are key porphyroblastic phases. They're growing syn to post tectonically with respect to our D2 event, so our S2 fabric. And what this means is that peak metamorphism is outlasting deformation. So let's just keep that in mind now when we move to the geochron. So here's a plot of previous geochron collected across northwest India. So the Suru Valley is up here, and you can see there's quite sparse data from there. And then we've got the Zanskar Valley and Himachal Pradesh. This blue bar here correlates to the average metamorphic GHS age range placed in these papers, and that's from about 32 to 15 million years. So that's our Oligocene to Miocene metamorphic ages. So what we can see from northwest India here, which is interesting, is that you've got a particularly much larger range and much older range as well. So it's dominated almost by Eocene to Oligocene metamorphic ages. Right, okay, so we've got the fabric development that's well constrained, so the early crustal thickening, and we can see that northwest India preserves a lot of these older ages. So it seems a really great place then to go and study the early evolution of the origin. So we're going to look at some different phases here. First off, we're going to look at titanite. So here's some backscatter electron images to see how it relates to the fabric. So remember that our peak pyroblast phases were syn to post D2, and we see similar relations with our titanite pyroblast here. So we've got a planar fabric that appears to be continuous with the external matrix S2 fabric here, but we can see that S2 fabric has been later refolded by a later event. And so that later event would be the development of the S3 fabric, and we can see in this backscatter image on the left here that the S3 fabric reorientates that titanite pyroblast and it wraps that titanite pyroblast. So what we take from this is that our prograde to peak development of titanite at lower grades is syn or post-tectonic with respect to that main fabric. At higher grades, we can see titanite preserved within garnet cores, so we infer that as prograde growth. But the main titanium oxide phases within the matrix are dominantly ilmenite and rutile. But we can also see titanite preserved in the matrix in some samples, and this we infer to be retrograde growth. So you have other titanium oxide phases, so you've got rutile cores, ilmenite rims, and then you can get patchy to polycrystalline titanite that is grows throughout the matrix there. And we infer that to be late, which is also supported by the geochron. Oops, there we go. So rather than showing a bunch of plots here, I've just summarized all of this onto a table. Anyone that's worked with titanite in the Himalaya will know that it can be a little bit bastard. So it's got abundant common lead, which results in quite large error ranges here. So our prograde to peak ages are around 36 million years, and that's in our syn to post D2 titanite pyroblast and in our garnet hosted ones. And then we've got titanite that I didn't show that's from the sillimanite and sillimanite K feldspar zone. That's about 23 to 22 million years. And then we've got that retrograde growth of titanite that's around 21 million years. So the titanite appears to basically nicely sort of bookend the beginning and end of the metamorphic development. Okay, so the other key phase is monazite, and I've just put up a few representative yttrium thorium X-ray maps here. Not all the grains are sort of so nicely zoned as this, but you can see some elevated cores and rims there. And so I've separated all the results by the grade that we saw on our isograds in the first map I showed. So here we've got garnet and staurolite. We've got our age range from 40 to 15 million years. And these are single spot ages collated from monazite. So we've got an age range here of about 28 to 23 million years from those two zones. Most of our results are from the kyanite zone here. So the coloring on these maps relates to the dysprosium-ytterbium ratio. So that's a middle to heavy rare earth element ratio. And we can sort of use that as an analogy for garnet growth and breakdown. So when garnet grows, it takes in our heavy rare earth elements. So increasing dysprosium-ytterbium ratios, we relate to garnet growth. And then when it breaks down, it releases that heavy rare earth elements back out. So lower ratios for garnet breakdown. So what we can see on this plot within some of our upper zones here, we've got elevated dysprosium-ytterbium ratios, which we relate to garnet growth. And then also in those samples over here as well. And so that age range is anywhere from around 28 to 32 million years. And that links nicely with the data, samarium neodymium data that's been collected from this zone, which again has garnet growth at around 28 to 32 million years. Load. Oops, there we go. Not much data from the sillimanite and sillimanite K feldspar zone, but the ages tend to be younger than 30 million years. And we've got one single age on the Luca Granite sample here at 20 million years. So obviously we've got quite a large spread of data there. What you'd expect to do, considering doing in situ work, is to then separate that based on the microstructure. So we've attempted that just with two samples I'm showing you here. So we've got one sample which has kyanite hosted grains and matrix hosted grains, and another sample with staurolite, kyanite, and then matrix hosted. And what we'd normally expect is that our older ages are dominated within the pyroblast, and then younger ages in the matrix, given monazite is quite susceptible to breakdown and reprecipitation. But what we can see is that there's actually not sort of a clear there's no clear sort of petrographic context to a distribution of ages there. What we can also see again is we've got sort of nice clear zones of increased dysprosium-ytterbium ratio. But the fact that we've got this changing trace element environment, particularly within the intermediate zone, indicates that, you know, we're probably not just getting two phases of growth and then getting mixing between those. We're getting sort of a large spread in our data here from continuous pulses of monazite growth throughout this age range. All right, so that's the data here just collated from what we've all been through. So the unfilled boxes here relate to the titanite, and then the single spot monazite ages, and these blue boxes relate to garnet growth. And then we've got our decompression and retrograde results here. So as I mentioned, we have prograde to peak recorded in the titanite, somewhere at around 36 million years. And then we've got a large spread in our data. So the largest spread is really around 35 to 18 million years, which is sort of parallel almost to some of the work shown yesterday by Sam. But we've also got one extra data point I just added in over lunch today, which I thought might be relevant, which is uranium-lead rutile analysis, and that's from a sample within the Zanskar Shear Zone. And I bring that in just to know that we know Zanskar Shear Zone, or the movement on the Zanskar Shear Zone, which is our South Tibetan detachment, is occurring sometime at around 22 million years. So this might indicate that decompression could be fairly rapid, but we've got to investigate this further. So let's come back now to that plot I showed you at the beginning. And so that's the average age range from the GHS. And that's the age range from this study using the variety of titanite and monazite results there. So even though we had that clearly constrained deformation framework, and we showed that we've got that abundance of crustal thickening, i.e. we're sort of the early part of the origin, we're really not getting some of those really old age ranges we see from elsewhere in northwest India. And so that raises a few questions for us. So what's the cause of that discrepancy between those other areas across northwest India and here? Is there a difference in tectonics between those zones that can account for that different age range? And how does this sort of play into a long strike variation across the whole GHS? Again, we've still got, you know, a fairly significant gap between when continental collision occurs and when we're getting our first monazite growth. So what does that mean? The results collected here might imply that we've got fairly rapid decompression occurring at the later stage of the origin once the Zanskar Shear Zone starts being active. But we're going to continue with our pressure temperature modeling. Here's one of my pseudosections on the right from the kyanite zone, to sort of hopefully deconvolve the rate of decompression and exhumation in the region. And finally, we've got this large spread in age range. So literally last week, we collected some split stream data on 2 samples, and we're hoping to further interrogate the trace element work there to work out when there might be pulses of growth related to different fibroblast development. All right, that's me.
Thanks a lot. Any questions? Bernardo?
Yes.
2 quick questions. First is, do you see any evidence of mapping at the highest grades?
Yeah. Yeah, so uniquely this area in comparison to other areas of Himalaya has fairly low amounts of melt. And so that is why we can preserve this greater abundance of the kyanite-grade zones. But yeah, when you get down into the sillimanite K feldspar zone, you get melting at sort of centimeter scale.
Thanks. And the second, can you clarify the relationship between the 2 aluminum silicates? Because you have two slides. On one, you have sillimanite outlasting kyanite, and in the second, you mentioned retrograde kyanite. So can you draw a PTT?
Was that the slides on the titanite? These ones?
No, before. The one with the relationship to the deformation phase.
Oh yeah.
Yeah.
So the reason why is your question basically why do you have syn to post sillimanite when you have post tectonic kyanite?
Yeah.
So the reason that is really is just based on what we could have observed in the microstructure is, in fact, I put in some extra slides for this. Here we go. So here's the relationship of the pyroblast to the fabric. The kyanite you see clearly overgrows the fabric. There's no warping of the S2 fabric here. Sillimanite, you have a lot of small, fine-scale fibrillite and some prismatic development, but it's not quite as clear from the microstructure that you can definitively say post-tectonic. So just to be safe, we've said that it's interpost there.
Thanks.
Dave.
I'm just saying I can help with that one actually, because I don't think it's in your samples, but in certain parts towards the Zanskar Shear Zone where there's been significant exhumation, the first stages of the exhumation are in the kyanite field, so you break garnet down to kyanite by instead of green.
What Suru said. What were you thinking?
Brown, that was orange.
Well, we're very close.
All right. Tom? So we started at low grades, and so our D1 fabrics were where we could see the original bedding structures, and then you can go from there to see when that fabric is refolded, and then we look at how it related to pyroblast. So the fact that we could sort of see clearly the distinction of how S2 related to the pyroblast allows us to sort of link together different structural zones and infer that they may be correlated in an overall sequence.
Are there any differences like the trend of the based on more macro scales? But folds.
No, I wouldn't say so. I'll have to think about that though.